Okay, 2.45 is a direct continuation of 2.44, so I would recommend you look at 2.44 first before going to this one. So we want to show that the number of nodes on stationary state 1D potentials always increases with energy. So intuitively, this is something that we know by heart, considering all of the examples we've seen of all the different potentials so far. And we're given a step-by-step series of solutions, or a series of problems to do in order to actually prove this mathematically. So we start by considering two real normalized solutions, psi n and psi m, with respective energies En and Em for the given potential V. So real and normalized implies that, we can't include sort of the complex exponentials with their weird behaviors, such as e to the ikx, because those are not normalizable. So we want to show this. To do that, hopefully this looks very familiar to 2.44. We're just going to do the same thing that 2.44 told us, which is that we start with the time-independent Schrodinger equation, negative h bar squared over 2m d, whoops, this is not a 2, there we go, d2 psi by dx squared, plus the potential V multiplied by psi is equal to the energy E multiplied by psi. So here, we're going to write this out in two forms. So we have negative h bar squared over 2m times d2 psi n by dx squared plus v psi n is going to equal E times psi n. And then we have the m solution, negative h bar squared over 2m times d2 psi m by dx squared plus v times psi m is going to equal E times psi m. So at this point, now we're going to do the thing that sort of problem 2.44 tells us to do, which is we're going to multiply the top solution by psi m, and we're going to multiply the bottom solution by psi n. So if we do that, then this is going to become negative h bar squared over 2m d2 psi n by dx squared multiplied by psi m plus v psi n psi m is equal to E times psi n psi m. And you know what? I forgot this is an En term as well. And then at the bottom, we're going to get negative h bar squared over 2m d2 psi m by dx squared times psi n plus v psi n psi m is equal to, and I should also include an Em here, Em psi n psi m. So now I'm going to add these two together, or sorry, subtract them together. And what I'm going to get is negative h bar squared over 2m times d2 psi n by dx squared psi m plus h bar squared over 2m d2 psi m by dx squared psi n. These two terms cancel, and this is going to equal psi n psi m times E n minus Em. And then let's move the h bar squared over 2m to the right hand. So what we get then is, let's see, d2 psi m by dx squared psi n, and I'm also changing the order here so the negative goes behind, minus d2 psi n by dx squared psi m. It's going to equal 2m over h bar squared psi n psi m multiplied by En minus Em. And at this point, hopefully this looks familiar because we also encountered this specific equation back in 2.44. We can use sort of the same property that we derived in 2.44, basically using the product rule and reverse engineering this, and this ends up equaling, once again, from 2.44, so look at that if you don't know how I get this, the derivative d psi m by dx psi n minus psi m d psi n by dx is going to equal 2m over h bar squared. I'm going to rearrange this, En minus Em psi n psi m. And if we look up, compare this, this is exactly what we get. So we're done. So once again, the specific method used to move this expression down into what this is via product rule. We covered this in 2.44, so if you don't know how this works, if you don't know how I can convert from this expression down to the expression over here, please look at 2.44. But we are done with part A. Okay. In part B, we want to show this property. Let x1 and x2 be two adjacent nodes of the function psi m, and we want to show this expression. So immediately, what I see here is that, this expression is shared down here, and the only thing that's different is that they're integrating from x1 to x2. So that tells me that I should just take this entire expression and integrate from x1 to x2. So let's do that. The integral from x1 to x2, d by dx, d psi m by dx times psi n minus psi m d psi n by dx. dx is going to equal 2m over h bar squared en minus em, because that gets brought out since it's a constant, times the integral x1 to x2 psi m psi n dx. So on the left hand, this integral is canceled out with the derivative, so we get, and I'm going to write d psi by dx as just psi prime, so psi m prime psi n minus psi m psi n prime, evaluated from x1 to x2, is going to equal 2m over h bar squared en minus em times our integral from x1 to x2 psi m psi n dx. So at this point, it's just a matter of plugging this in. So we get psi m prime of x2 times psi n of x2 minus psi m of x2 times psi n prime of x2, and then subtracted by psi m prime of x1 psi n of x1 minus psi m of x1 psi n prime of x1 so that becomes this. Next, immediately recognize, x1 and x2 are nodes for psi m. So by definition, nodes are where psi m equals 0, because nodes are the zero crossings on a wave function. So all of these psi m terms that have an x1 or x2 go to 0, because psi m of x2 is going to be 0 by definition of x2 being a node of psi m. Over here, same thing. Psi m x1 is going to be 0 because of x1 being a node of psi m. So what we're left with is psi m prime x2 psi n x2 minus psi m prime x1 times psi n x1. And this is going to equal 2m over h bar squared times en minus em times the integral from x1 to x2 psi m psi n times dx. And if we look up above at this, do we match it? Psi m prime x2 psi n x2 minus psi m prime x1 psi n x1. We do indeed match it. We have solved part B. Okay, final part in C. We're saying that if psi n has no nodes between x1 and x2, then it must be the same sign everywhere in the interval. Show that this conclusion then results in B leading to a contradiction. Therefore, between every pair of nodes, psi m and psi n, there must be, or therefore, between every pair of nodes of psi m, the higher energy wave function psi n must have at least one node. In particular, the number of nodes increases with energy. So let's start, before looking at the bottom part, by proving the first part, which is that if psi n has no nodes between x1 and x2, then it must have the same sign everywhere in the interval, therefore resulting in B leading to a contradiction. So let's look at the behavior of psi m and psi n first. So suppose that I have a point. Let's say let's draw psi m in let's draw psi m in black, and let's draw psi n in red. So there's a few possibilities here. First off, there's the possibility of the node psi m being a positive node. So psi m looks something like this, and then psi n is either positive psi n, so positive, or psi n is negative. Alternatively, the node can be a negatively peaked node. So the two peaks, or the two nodes, are like this, and then psi m looks something like this, and then the negative, and then we have, once again, you know, a positive psi n and a negative psi n. So for a positive psi n, it could be some weird thing like this, and then for a negative psi n, some weird thing like this. Same thing here, positive psi n, some weird thing like this. Negative psi n, some weird thing like this. So once again, we're considering the case where psi n doesn't have a node between the two nodes of psi m. So that means psi n doesn't have a zero crossing. It does not cross the x-axis, so it just stays above and looks something like this. So these are four different possibilities. So let's look at case 1. So in case 1, we have positive psi m, positive psi m prime at x1, because this is x1 and this is x2, x1 and x2, and then negative psi m prime at x2, because if we look at the derivative, it's increasing and then decreasing, and then we have positive psi n. So let's take this expression and see what happens to it. So this is a positive term. Psi n is a positive term. Or sorry, my apologies. That's psi m prime at x2. So psi m prime at x2 is negative. This is a positive. Psi m prime at x1 is going to be a positive. Psi n is always a positive. This entire term is going to be a positive because en is always greater than em. Then we have psi m and psi n, which are both positive. So we have a negative subtracted by a positive, so some negative constant subtracted by some positive constant, or not a constant, but some negative thing subtracted by some positive thing, is going to equal some positive thing. So that's obviously a contradiction, because a negative thing subtracted by a positive thing is going to be, once again, another negative thing, and that's going to equal a positive thing. So that obviously doesn't work. Case 1 is false. This cannot happen. Next, let's look at case 2, which is going to be the same thing, but we're looking at the negative psi n instead. So case 2, we have positive psi m. We have positive psi m prime at x1. We have negative psi m prime at x2, and then we have negative psi n. And then once again, we bring this expression down. So I'm just going to copy paste this again. And let's see, this is going to be psi m prime at x2 is once again negative. This is negative. Psi m prime at x1 is going to be positive. This is still negative. And then this entire thing is positive. And then over here we have psi m, which is a positive, and psi n, which is a negative. So this is going to be some positive constant. So let's call this, or not a constant, I'm sorry, I keep on calling it a constant, but some positive thing, let's call it a, subtracted by some negative thing. So this is going to be plus another positive thing, b, and this is going to equal some negative thing, c, negative c. So once again, we have another contradiction. A positive is apparently equal to a negative. This also doesn't work. Now, let's look at case 3, which is over here. It's going to be this downwards, this like negative sort of mound, and then let's look at positive psi n. So this is going to be negative psi m, and then the derivatives are going to switch signs, so it's going to be negative psi m prime at x1, and then positive psi m prime at x2, and then we have positive psi n. Bring this down once again. And let's see. We have psi m prime at x2, which is positive. We have psi n, which is positive. Psi m prime at x1, which is going to be negative. Psi n at x1, which is going to be positive. This entire thing, once again, is positive. Psi m is going to be negative. Psi n is going to be positive. So we get some positive thing, A, subtracted by some negative thing, which is going to become added to some positive thing, B, is going to equal some negative thing, negative C. So once again, this doesn't work. Case 3 cannot ever happen. Now let's look at case 4. So it's the exact same thing. Negative psi m, negative psi m prime at x1, positive psi m prime at x2, and then this time a negative psi n. So we're looking at case 4 where both psi n and psi m are negative. In this case, what we're going to get, psi m prime at x2 is positive, psi n is going to be negative, psi m prime at x1 is going to be positive, or sorry, negative. Psi n at x1 is going to be negative. Is that right? Psi m? Yeah. And then this entire thing is positive. And over here we have a negative multiplied by a negative, because we have psi m and psi n both as negative. So this is going to be some negative thing, negative A, subtracted by a positive thing. So subtracted by some positive thing B. And this is going to equal some positive thing C. So once again, this is a negative and C is a positive. This also doesn't work. We have shown that every possible case of psi m and psi n being any possible combination of signs always results in this statement having a problem. Therefore, psi n always has to have a pair, psi n always has to have at least one node between adjacent nodes of psi m. And now let's look at graphically what that actually represents. Okay, so to actually show the significance of this requirement that the higher energy has to have at least one node between all of the adjacent nodes, let's do an example. So let's suppose I have an infinite square well. Oops, I should use just something like this instead. Yeah, so let's suppose that I have an infinite square well and the walls are located around here. And let's say that psi m is in black, and let's say that psi m has two nodes. It has a node here, and it has a node here. So in that case, or actually no, you know what? Let's say it has three nodes. So in which case it looks something like, because the infinite square well, it has to equal 0 on the edges. So it equals something like this. There we go. And now let's look at psi n. So psi n by definition has to have at least one node in between each adjacent node. So there has to be a node here. There has to be a node here. Also, it has to sort of go to 0 on the edges as well. So let's see how. So the thing about psi n and psi m in general is that these are sinusoids. So the whole point of a sinusoid is that it's sort of periodic. It cannot sort of change its shape over time. It has to maintain the same constant pattern. So if we look at this, the fact that there's two nodes here automatically implies that there has to be additional nodes as well. Because of the fact that, you know, psi n is periodic, it has to sort of go back to default after every, effectively, cycle. So what that automatically implies that there also has to be a node here, and there also has to be a node here. And if we look at this, immediately there seems to be a problem, because if the nodes look something like this, that sort of implies that the wave function looks like this. And that's obviously not allowed because it's not going to 0 at the edges of the well. So what that further implies is that actually there's also nodes here, here, and here. So the wave function looks something more like this. And this drawing has become horrible, but that's sort of the main point, in that Very obviously, psi n, since it has a higher energy, is going to have more nodes than psi m, and we see this via the sort of the requirement, which is that between every node of psi m, there has to be at least one node in psi n, and then we also have these additional nodes on the nodes of psi m, as a result of sort of psi n having this requirement that it's a sinusoid and therefore has to be periodic. So if we put the nodes directly in the middle, that actually adds additional required nodes directly on the nodes of psi m as well. And then you can try this out with a bunch of different ways. You can instead of putting the nodes directly in the middle, you can offset the nodes slightly. As long as sort of everything is periodic, you will always get a wave function that sort of is going to have more nodes than the one that with the lower energy, as long as you sort of apply this condition. And just remember the fact that, since this is a sinusoid, it has to be periodic, it has to follow a constant pattern. So your nodes have to be evenly spaced apart, and it sort of, if you add on the condition of the infinite square well, which is that, it has to go to 0 at these endpoints, that also adds an additional level of constraint. Alternatively, you can try this with a finite well. The whole point, the same thing applies. You'll get the same result, just like the resulting wave function you get might look a little bit different based off of what type of parameters you have. The type of potential sort of might change what kind of wave function it looks like. But in general, sort of the major point here is that by having this condition that between each two adjacent nodes, there's a node for the higher energy, or at least one node for the higher energy, you're always going to get a resulting higher energy wave function that has more zero crossings compared to the lower energy. And with that, we are done with this problem.